Louder. I can mumble louder. Brilliant. Okay, so hopefully everybody managed to navigate the Blackboard site. You can actually do the pre-class assignments and the in-class assignments. I'm never sure if I should actually leave some time here to do it now or if you just prefer to do it at home. Frankly, that's up to you. Today we talk about the science of astronomy, and mostly I'm going to get you all on a right footing for the sense of scale. So astronomy is three things, and hopefully I'm going to talk about the three main ingredients for the first 3 weeks. That was my whole idea. Next week we'll talk about light. We learn everything we can about astronomy from light, from stars, from galaxies. Anything that comes out of we've learned about stars and the whole universe comes from the information that's encoded in light. So we'll talk about what light can tell us. Next is gravity. There's four forces in physics, but really in astronomy you only have to worry about one. It's gravity. It's the only one that works on the scales that we're going to talk about. And the third thing is the fact that we have huge scales to deal with. It's both really far away, but also the universe is very patient and very, very old. So if something takes 1 million years to do, that's actually a blink of an eye for most of the processes in the universe. So you can actually do things slowly and you will still get there, despite the fact that it's really large scale. So I'm trying to get these three concepts across, and really that keeps coming back. It's either gravity, we learn something from light, and oh look, the scales are huge, right? So this comes back over and over and over again. So hopefully before the class you saw crash course number 1, the pre-class assignment. How do you like all the videos? Are they any good? Yeah, I really like Phil's videos. So I'm going to try to expand a little bit on what he's been doing. So we'll talk about what is astronomy, what kind of science is it, who is an astronomer, who can be an astronomer. So what are we focusing on, and then communicating the scales of large numbers as well. And then one thing, and this is all science educators everywhere, this is the communication part of this class. If you are communicating, if your team is communicating to another team, use the units. Always use the units. If you go like, no, we've been talking about this in kilometers for like ever. We know it's a Canadian team. We've sent everything in kilometers. We know, like, I don't need to specify that. And the next thing you know, everything they've done is 1.6 times bigger because they thought you were talking in miles. So it's really important to communicate in units. It is something about redundancy. All right, so what is science? So astronomy is a science, but a science is a system to approximate, to get ever better at understanding reality. It isn't equivalent to reality. It is our system of thought that we have come up as a society to better understand what reality is. And if you open a newspaper or online, I'm assuming, or you look at any kind of news lately, you're seeing science in action. We have a reality. This is a reality while we're all wearing masks and being so far apart, but we're actually seeing science in action, making mistakes, figuring something out, what's more important. So science is something where we start with a hypothesis, and the hypothesis is the idea that you can test. You hear people say, oh, it's only a theory. No, a theory is one that we've tested already. A theory is something that already got a couple of things right. And then you can test it more further. You can always keep testing. We keep testing Einstein's theories of gravity and space. And that's fine, because first we need to see where it breaks. And so a hypothesis is something that I haven't tested at all yet. I have a bright idea. I think dark matter is all space gerbils, right? That's my bright idea. That's my hypothesis. It becomes a theory as soon as I have some evidence for the said space gerbils. If I don't have that, it stays a hypothesis for now. Just a theory. A theory is already something that has been proven a couple of times. It's definitely not a belief system, and the best scientist, if you are being a good, conscientious scientist, and you have your favorite pet theory, space gerbils, then as soon as I see evidence against it, they would all suffocate. I should change my hypothesis. I should change my belief system. That is not to say that scientists aren't human and they have their pet theory or hypothesis that they really are having some trouble letting go of. That's fine, but actually most of the time we go, oh, that's different? Okay, cool. I don't have to worry about that part anymore. Astronomy is an observational science, so that is something that we have in common with a lot of social sciences, for example. We're looking at a complex system and we can't really mess with it. In the case of social sciences, you don't mess with the system because, well, that would be cruel because the system is made out of people. But in our case, we can't mess with it because, well, it's really far away. I can't even touch it. So we only can see what we see and explain our observations. We can design observations. We can design a way of looking at it. We can look at it with different telescopes at different times, for example. We can design that part. We can design the way we look, but we can't design the thing we're looking at. Like that's nothing that we can change. So we can only experiment, or we can't change the experiment. This is a really weird thing for anybody who's, for instance, a chemist. Because, well, just run it again and now, up the temperature by a couple of degrees. Yeah, I can't do that, right? If the event is gone, the event is gone. If there happen to be clouds, well, you're just out of luck. So, astronomy learns, now this is a fun thing. This sentence is slightly out of date. I love this about astronomy. My 100 level class regularly gets out of date because we found a new thing. This should now really say astronomy learns almost all it can from light, electromagnetic radiation. We now have a few more ways that we can learn about astronomical events. But for the vast history of astronomy, we learned everything from light, and in fact, most of it from light that we can see. So we cannot change the experiment. This can be very frustrating. So we observe, deduce, form a theory, and then test predictions. Best part is when you go like, well, this star is fluctuating this way. It should possibly explode. Maybe who here has heard of the star Betelgeuse? Yeah, it's a fantastic Arab name. So it was dimming about a few months ago. Time's weird now at the moment, but I'm pretty sure it was still in 2020. And so it dimmed a little bit, and it was a bit of a mystery. You could actually go see Orion, and you watch like that star is visibly dimmer. And so the stellar people actually dove on top of it. It's like, is it about to explode? And yeah, odds were against us. So the model said, no, probably not. We're probably fine. If not, then we're going to see a really bright star. So that'll be cool too. It is going to explode, but somewhere in the next 100,000 years. So stay tuned. So you make predictions and you see if you can come up with something that you can then test. This is something that I'm trying to avoid. If everybody feels like a helpless tiny little speck, or if you have vertigo, close your eyes, breathe deeply, and keep going, because this dome can give you some vertigo. The scales can give you some vertigo. That's okay. To me, it means we're a very important little speck, because we're the specks thinking about it. What I'm not trying to do, and none of these things are correct, by the way. This is very much a science cartoon, saying that how many different words we have for things. This happens in sciences because we needed a new word for the weird thing that we just found. And sometimes even the word is not that descriptive, but well, at this point we've been using it for 10 years or 100 years or what have you. I'm trying not to teach you a lot of new terms. There will be new terms. There are certain Astro 100 classes where you learn as many new words as you do in French 100, and I'll try to avoid that. But other than that, we have lots of strange terms for things, and you might come across a couple. You will come across. Right, minimal dead white guy content. This is a philosophical part of how you teach science. Maybe some of you have had this kind of science textbook where there's all these little sidebars about these really interesting people who did all these fantastic things, and it's a little bit of that hero narrative for scientists, the brilliant, usually man, who did the thing. It's completely inaccurate as far as how science goes. Yes, somebody made a clever contribution, but it was always part of a conversation. You cannot go back far enough. So you can go back, for instance, like the beginning of the modern astronomy, Galileo Galilei, and you go like, well, there's a brilliant dude. He's like completely on his own, fighting against the church, right? You'll hear that narrative. Then you look at his correspondence. He was writing letters to literally every other university in Europe. So basically, as far as he could send, he didn't have email, so it was like correspondence would take months. Yeah, it all took slower time, but he was part of a larger conversation. He got observations from other people contributed ideas. It is always an exchange. So I'm not a big fan. I wasn't a big fan as a student of the sidebar where you have like this big mustachioed man with like stuff that he possibly or not could have done. In fact, this is the third hit on awesome mustache on Google, but it always seems like the same thing. So I'm going to avoid that where I can. Is that okay with you? Good, because that frees up a ton of time. So these are the topics that I want to talk about in this semester. We're going to go about what is science, that's sort of what I've been talking to you about now. Next week we'll talk about light, because we learn just about everything from that, but I also will talk about something that we now call multi-messenger astronomy, because certain things travel just about at the speed of light, and if we can detect those, like gravitational waves or high energy particles, then we actually can learn about very exotic things that way as well. So light and information really. And I'll talk about gravity. Again, that's the only way that's the only force that really matters in the universe at the moment, because gravity is the only one that works at really large scales. We'll talk about the scales and times of the universe again in week 4. The night sky, so what can you see, right? That's how we got started. But I want to talk about these three main themes. These keep coming back in astronomy. And then we'll start at the night sky. Of course, we'll move to stars. Then we move around the planets around those stars, and then including the ones nearby, which basically is the solar system. So I don't do the normal astrophysics 100 scaling thing where you start at Earth and then get bigger and bigger and bigger, because there's so much interesting stuff in our solar system, and we find new things on Mars like every other week. So I'll get all enthusiastic, spend 3 weeks talking about Mars alone, and then I'll have to throw in the rest of the universe at the end in last week or something, and that just does not work. So I don't want to run out of time, but you should also think of our solar system as just one example of many solar systems that we know about now. And then we talk about telescopes, because how do we actually identify the light? I'll talk about galaxies, which is something that I work in, and then cosmology, which is the whole universe as one thing. So cosmology is like, how does the universe act? How does it going to end? How did it start? What is it? How is it as a whole physical system? It's the largest physical system that we know of. So those are the scales that I want to talk about. Hopefully you've seen this now. So who is an astronomer? Who still has their voting cards with them? Ha ha ha. You thought this was going to be all passive, but no. You're going to have to whip out your voting cards every time here. So I have these things in the in-class assignments, so you can do them again, but I really want to get a little bit back from you, because right now you're just a bunch of masks in the darkness there. So, all right. Who is an astronomer? Anyone who owns a telescope, professionals with a PhD in astrophysics, anyone who examines the night sky, or people who work for NASA. Let's see, voting in 1, 2, 3. Sea of green, thank you. What is astronomy? The study of the night sky and the motions of stars and planets, the science of planets, stars, galaxies, and the universe based on observations, the study of anything that happens in space, and predictions on how planets and constellations affect people's lives. All right, let's see. Voting in 1, 2, 3. See, this is when I see a mix, and I would usually say, go confer with your neighbor, but your neighbor's like 6 feet at least away. So this is something where I was not maybe as clear, or maybe the video wasn't as clear. So I want you to go think about that one, because which one of these would make the most sense, right? So is it just stars and planets in astronomy? Or is it actually planets, stars, galaxies, and the universe, like basically everything up? Or is it studying anything that happens in space? Because space is a very specific thing. It's like where we send astronauts, but it's not necessarily all the way to the end of the universe. It's quite a bit longer. And predictions on how this stuff affects people's lives, that is what we call astrology. Look, if that gets you to eat a salad, great. If somebody actually wants your credit card number based on that, please don't give it. That's my end of astrology rant. All right, so using the correct units. So this is almost the science blooper reel. It's critically important. And again, this is not just I'm a stickler for these things. I'm a stickler for these things because I got burnt. That's the subtitle for this. I do want you to actually identify what you're using. So if you go like, oh, I know which equation to use the units. And if you're underlining your answer, but use the units. Otherwise, I'm assuming gerbils. Otherwise, I'm just going like, it could be anything. Could be absolutely anything. So you're not done talking until you've put the units at the end of your answer. This is important because, we wouldn't be NASA if we hadn't like an embarrassing story to explain why. In 1999, Mars Climate Orbiter was sent to Mars is now within NASA and other in other space agency circles known as the planet that eats your probe. It has had the most probes sent to it, and also about half of them make it there. A lot of them die along the route. And in this case, it was supposed to start, one piece of software used imperial units, while another piece used metric units, and they didn't communicate the units. It was a cost-saving measure, because usually at the end of the project, we stick every head engineer and they could buy every little thing and make sure that the units line up. But we didn't need those for plane tickets, so yeah. It's a very expensive piece of junk in space now. And the problem is that Pascal, which is a pressure unit, and pounds per square inch look about the same. They go from about 0 to 100. So both of them kind of go between 0 and 100. I've done it. I can guarantee you that if any scientist thinks about it long enough, they probably have skated over a thing where they forgot about the units. There's so many units, and typically because we have imperial and metric, at the beginning of a project, you go like, all right, we're all using metric. I don't care if you like imperial. I don't care if everything you've written so far is in imperial. This is the one we're using. So there's a communication up front, a communication during, and a communication afterwards. This is the habit I'm trying to get you into, right? As future scientists or journalists or educators or whatever you want to do, units are going to be important. If you're going to be a nurse, you want to know if it's milliliters or not, right? That's important. We have historical examples. For example, this is the Vasa, which is in Stockholm. It's a fantastic museum, but it sank really, really quickly right at the beginning because it was completely off-balanced, and that was because the timber work on either side was measured in 2 different kinds of feet. This is back when almost every city had a different definition of the feet, and they could switch by more than an inch. You could really get shrifted if you were ordering something in one size of feet and it arrived in the other, for example. Aviation is another example. All aviation in the Western world still uses imperial units, so it uses gallons, feet for altitude, and nautical miles, not the miles that you see on your dashboard in your car, nautical miles for distances. Except if you are, the pump, and the pump basically now says it in liters. And I can assure you that if you paid for gallons and you're getting it in liters, you're going to get stiffed. That's a 3.7. There's 3.7 liters in every gallon, so you're definitely getting the short end of the stick there. And so that's what happened to the Canadians. There's a whole bunch of stories that you probably don't want to know as frequent air travelers about what goes wrong when, for instance, a Russian plane comes into US skies, because all the Russian gear is all in kilometers and meters. So, for example, they have been known to fly at 30,000, not meters, like at 10,000 meters instead of the 10,000 feet where they were told to go, right? That's a factor 3 in difference right there. So, yeah, telling you exactly what unit it is really super important. So we'll stick to Système International, which is, as you can tell from the phrase, is a French-based system back from Napoleon. It's all in distances. Our lengths are in meters, kilograms, seconds, and then Kelvin is our temperature. Those are the ones that are really important in astronomy. So those are the ones we mostly be using, but they're all kind of interconnected. They're all defined based off each other. And so we have a whole bunch of different things that we also measure for, like electricity, all these good things. There's some derived, like Joule and Watt, those for energy and work, and Newton for force. So if you are going to do Physics 200, for example, we definitely use those. And so why do we do that? It's because the entire world already adopted the Système International. I'm sorry. We also do these standard prefixes, and I think you're a little more, I'm a little more mega and giga and tera. Those are things that you probably already know about. As soon as you have like a data plan, you have so many gigabytes, right? A byte is the unit of storage. So it is, deca is 10, hecto is 100, kilo is 1,000, mega is a million, and then giga is a billion, and then tera is 10 to the 12, so it's 1,000 billion. So you can keep so you can actually scale things up easily. Kelvin, again, that's a physics thing. It's simply because 0K is absolute zero, and the space is quite cold. It is not entirely 0 Kelvin, but it is 3 Kelvin above, well, 2.71 above absolute zero. Absolute zero is when all the molecules basically stop. You've frozen everything. So that's a good point to start at 0, and then you can see how many Kelvin. So all temperatures will be reported. All temperatures of stars are reported in Kelvin. So typically you're working with like this kind of star. So the visible surface of the sun is about 6,000 Kelvin. Sirius is a lot hotter. It's about 10,000 Kelvin. And then the core of the sun is 60 million Kelvin. And then that's why we actually study nuclear explosions, if we want to understand how stars' interiors work, because that's actually as close as we'll get to one. So hard little leather-necked about it. So we have our own units for certain things. Most importantly, solar relative units. Is solar mass and solar luminosity. If you start counting things like how heavy the sun is, it's 10 to the 30 kilograms. That doesn't really scale. So you go like 1 sun, 2 sun, 3 suns. That was the easiest thing to do. So we use the sun as a standard measure. We use light years occasionally. You'd be surprised how little I actually use light years for distance, but it is the distance that light travels over a full year. So for example, our sun is 8 minutes away in light travel time. And then you can, I think at the moment, Voyager 1 is 26 light hours away from us. So it says a little bip, and 26 hours later we receive it. And so you can imagine how long a light year is. It's quite a distance. We also use the astronomical unit. That means the distance between Earth and Sun. And that's a really useful for when we're trying to measure distances into the universe. And then parsecs basically derived from these two. Angstrom is something that we use for wavelength for light that we receive. So it's like 10 to the minus 10 meters. Nanometers is 10 to the minus 9. We use both. Okay, a test already. I put a this whole course, pre-course test. I just want to know how you guys, what do you know right now? I mean, some of you might be, I don't know, a chemist that has a specialty in laser measurements, and so all the stuff that I say about light is like child's play to you or not. I don't know. So I'm trying to figure out what you guys know already, and then we'll do a similar test at the end of the class, and I'll figure out how well I did the teaching. All right, this is just for me, but it will be an extra credit for you if you do both of them. Okay? It's on Blackboard. You should be able to do it as of this week, please. Okay, so again, I'll try to stick to not talking for longer than about half an hour because, well, A, I get really sick of it, and you must be too. So I'll talk about the scales of the universe. This is something that a colleague of mine made, Daniela Breshkov, who's in University of Western Cape. No, University of Western Australia. It is a view of the universe where you try to get a feeling of the scale. So this is, your face is about 10 centimeters across. You're about, the scale of a meter or two. 10 meters is, the patio. 100 meters is kind of the buildings. That's like the campus is about 1 kilometer. And then this is Google. So Googleplex 10 kilometers is about the city size. 100 kilometers, getting close to like a state size. 1,000 kilometers, yeah, that's like that's we're a continent. At 10,000 kilometers, we're at the size of the Earth. So these are steps of 10, right? And then 10,000 kilometers, a million kilometers, Earth, Moon, goes really fast in these steps of 10. You can go really big distances. There's 100 million kilometers. Oh, look, this is the inner solar system. 1 billion kilometers, outer solar system. And there's our furthest probes. 100 billion kilometers, we actually start getting to the edge of our solar system where all the comets live. A light year is kind of like the edge of our solar system. 10 light years, we're already at the nearest stars. 100 light years, these are all the visible stars. 1,000 light years, we're well beyond all the visible stars with the naked eye. At 10,000 light years, we're seeing the structure of our galaxy. 100,000 light years, there goes our galaxy. And then a million light years, the nearby galaxies. 10 million light years, we're definitely looking at nearby, easily observed galaxies. 100 million light years, we're actually in the fluffy structure of the entire universe. So every little point here ends up being a single galaxy. So you have this whole, whoa, and then we drop all the way back down. I can't talk this fast, but anyway, we drop all the way back down in scale, right down to our little blue marble there, all the way down to Google. I'm having motion sickness, you must be too. Back to our eye, because there's a similar number of, down to 1 centimeter we see the eye, the human eye. 1 millimeter we're down to the retina. Micrometers we're seeing actually blood vessels. 10 micrometers, that's actually blood cells. 1 micrometer we're getting down to DNA, chromosomes. 100 nanometers we start seeing strands of DNA. 10 nanometers we see actually what the molecules that are make up DNA. Nanometer we're going into an atom on the molecule. Here's electron orbits, about 10 picometers. These are the inner electron orbits, and then we go down and down and down and down and down. What's that little, that's the nucleus of the atom. Down to femtometers, another step smaller, another step smaller, and that's as small as our physics go. See, the fun part is, not only do we have several steps going to the larger scale universe from our human scale, there are that many steps down to smaller scales, and the trick for physics is to explain everything from the smallest scales to the larger scales. If the story doesn't line up, if a scale doesn't work, then our theory is still rattling. That still doesn't work. So, interestingly enough, at the smallest scale, we talk about quantum mechanics. So a lot of things that happen at the very smallest scale deal with quantum mechanics, and how quantum mechanics actually explains how vacuum, so absolute nothing, behaves, and how we understand how the biggest scales work are now kind of coming back together, because at some point the whole universe was only a femtometer across, right? At some point, right after the Big Bang, it was tiny. And so we have to come up with a story that works for both the smallest scales and the larger scales. So the scales are important. I'll be talking about anything bigger than a human. The other part is other physics. I really have it doesn't have a good word for bigger, biggest, and more bigger. So I'll keep using huge, and doesn't really convey how much bigger it is than, say, the huge I was talking about earlier. So I just say in biggin, and more importantly, I'll try to put a number on it, right? So this is in the App Store, I think. So you can use, for instance, the Rice problem. So scientific notation. Who here has done anything in scientific notation? 10 to the, oh, cool, fantastic. All right, so this is the thing that I want you to get comfortable with, right? Things that are 10 times bigger. Who here has heard of the pH scale? Right? Yeah, we've all got, like, my mountain fountain water has like 0 pH. Fantastic. But what does it mean if your pH shifts a bit, right? That's a step of 10. That's not it's not twice as acidic. It's 10 times more acidic as soon as you move 1 full digit on the pH scale. So for the Rice problem, I really like this one because it kind of gives you its exponential growth. If you ask for a rice grain on the first one, 2 rice grains, double it on the next one, double it on the next one, by the time you get over here, you have 2 times 10 to the 64th. You go like, that can't possibly be that much. It is, it's 100 billion tons of rice, and I think it's like the full rice production of every rice-producing country for a decade. So, yeah, that's a good way to over-ask. And it really illustrates that if you have an exponential thing, if something grows exponentially, which means that it doubles every step, it blows up very, very quickly. And we have this, well, we're having this right now, because that's how epidemics work, but it's also how bacterial growth can work. It's also how like a whole bunch of how fast a star consumes its last fuel, for example, is also exponential. And as soon as that works, there's no fighting it. You basically are going to lose. So 10 to the power is how I'm going to try to express scales. Okay. I like this one because it kind of shows, A, both how New Yorkers think about the rest of the country, and B, what an exponential scale is, right? So because the first step is 1 block, the second step is all the blocks left of the Hudson River. Then there's New Jersey, which we will not talk about, and then there's another step which is accidentally the entire country, and then Pacific Ocean, and then Japan, right? These are steps of 10. The joke is that essentially you think of like, well, 1 block is fine, this is already too far, and I can fly to Japan because it's not that far further, right? It's steps of 10 that they're taking. The same thing you can do for, I like XKCD, so I'll have occasionally that in there. 1 meter, 10 meters, 100 meters. So every step is another factor of 10. So you can go from how tall buildings and mountains are to the edge of the observable universe in a reasonable number of steps, but still a whole bunch of steps of 10, right? So you can start down there as like, this is space, but there's still a whole bunch of more space. All right, so we're going to do this now in the planetarium. I forgot my planetarium slide. I probably can stop the recording because I've noticed that if the recording goes for the planetarium, you just see you just see this little dot here, so that's not really going to enrich your life.